This lecture will be focusing on chapter 1.4 to 1.8. So the birth of chemistry. So the Englishman Robert Boyle is considered to be the father of chemistry. So Boyle provided clear evidence for the atomic makeup of matter. This is back in the 1600s. So Boyle's theory was that elements cannot be chemically broken down. Many different elements can exist, and that elements can join together to form chemical compounds. And so moving on to the late 1700s, Joseph Priestley did some work on chemical compounds. So chemical compounds are a substance formed from two or more elements chemically united in fixed proportions. So Priestley's work was looking at mercury oxide. So if we take a look over here, we can see that heating mercury oxide, which is a solid material here, when you heat it up, it yields a liquid metallic mercury, and then it produces oxygen gas. And so these chemical components are composed of fixed combinations of constituent elements. So there was one material, the mercury oxide, that looked like it was just a single material, but when you heat it up, it can be decomposed into its chemical components. So chemical formulas are defined as the standard format for describing each compound using the symbols of the constituent elements and the subscripts to indicate the number of atoms of each different compound. So if no subscript is given, then one atom is understood. So for example, for mercury oxide, HgO, so Hg is a symbol for mercury, and then O is a symbol for oxygen. So since there's no subscript for either one of these, so that stands for one mercury atom and one oxygen atom in fixed proportion 1:1. O2, that's the symbol for oxygen, and 2 means that there are two atoms. So that oxygen molecule has two separate atoms of oxygen. H2O, H is hydrogen, O is oxygen. Here this means there's two hydrogens, one oxygen. So on, up to some more complex molecules. So a chemical equation is the standard format for writing a chemical reaction, where on the left-hand side we have what are called reactants, and the right-hand side we have what are called products. And there'll be an arrow in the middle that indicates the direction of a chemical transformation. So let's consider the chemical formulas and the chemical equation for the mercury oxide heating experiment. So if we take a look here, we can see that we have our reactant, mercury oxide, which we can put as a solid, heats up to form Hg, which is mercury, as a liquid, plus O2, which is oxygen, as a gas. So on the left-hand side, this mercury oxide is the reactant. And on the right-hand side, both of these guys together are the products. Okay, so we have this chemical reaction between mercury oxide, reactant, and we have the arrow in the middle showing that a chemical transformation has happened to form mercury and oxygen. So then moving on, the Frenchman Antoine Lavoisier discovered the law of mass conservation. So the law of mass conservation states that mass is neither created nor destroyed in a chemical reaction. In such, the mass of the reactant, so what's put into a chemical equation, is equal to the mass of the products that comes out. So if we go back to our idea of Priestley's heating up of mercury oxide, we can illustrate this law of mass conservation. So if we go back up to our equation, if we see that 3 grams of this mercury oxide is heated up, and it's shown to produce 2 grams of this mercury, we ask the question, how much oxygen gas is formed? So an unknown amount in grams. So the law of mass conservation states that the amount of mass that we start in the reactants is going to be equal to the amount of mass that we end in the products. So therefore, we know that 3 grams is going to be equal to 2 grams plus some unknown x. So we can rearrange to our algebra here, say that 3 grams minus 2 grams is going to be equal to 1 gram. So our final answer would be that 1 gram of oxygen is formed. Okay, so to make this a little more of an acceptable answer, we would say 1 gram of O2 is formed. So this leads us now to the law of definite proportions. So the French chemist Joseph Proust developed a law of definite proportions, stating that different samples of a pure chemical compound always contain the same proportions of elements by mass. So, meaning that the elements combine in specific proportions, not random proportions. So, for example, if we take a look at water, H2O, so we have 2 hydrogen atoms and 1 oxygen atom. If we take a look at about the mass constituents of the two, there's always 1 part hydrogen by mass for 8 parts of oxygen by mass. For carbon dioxide, where we have 1 carbon, 2 oxygens, contains 3 parts carbon by 8 parts oxygen by mass. Again, the important part of this law of definite proportions is it is by mass. Okay? And so no matter what water molecule or what carbon dioxide or what any chemical you look at, it will always have the same proportions of its constituent atoms by mass. That leads us now to the law of multiple proportions. So the English school teacher John Dalton discovered the law of multiple proportions, which states that elements can combine in different ways to form different chemical compounds, whose mass ratios are simple whole number multiples of each other. So matter is composed as discrete atoms of characteristic mass that combine in specific well-defined ways. Okay, so nitrogen and oxygen can combine together in a 7 to 8 mass ratio to form nitric oxide, or nitrogen and oxygen can combine together in 7:16 ratio to form nitrogen dioxide. So the first compound has exactly twice the amount of oxygen as the second compound. So down here we can see that corresponds to 1 nitrogen, 1 oxide for nitric oxide, and 2 oxygens to 1 nitrogen for nitrogen dioxide. Okay, so you guys don't need to memorize these specific mass ratios for nitrogen and oxygen. Just know that the law of multiple proportions means that atoms can add together in different ways. So Dalton then, after developing his law, he took all of the information that had been proposed to that point and combined them together to form Dalton's atomic theory. So this is definitely the most important thing that we've covered thus far in our lectures. And so you will need to know all 4 of these different components. So Dalton combined the 3 laws together, the law of mass conservation, the law of definite proportions, and the law of multiple proportions, to form his atomic theory. So number 1 on Dalton's atomic theory, elements are made up of tiny particles called atoms. 2, each element is characterized by the mass of its atoms. The atoms of the same element have the same mass, but atoms of different elements have different masses. The chemical combination of elements to make different chemical components occurs when atoms bond together in small whole number ratios. And 4, chemical reactions only rearrange how atoms are combined in chemical compounds. The atoms themselves do not change. Okay? We're made up of atoms. Each element has its own mass. Chemical compounds are made of a fixed ratio of atoms, and that chemical reactions only rearrange atoms. The atoms themselves do not change. So, but that begs the question now, what is an atom? So that leads us to a couple very important experiments. So first was the discovery of an electron. So the English physicist J.J. Thomson set out to determine the composition of an atom. And so his seminal experiment was the cathode ray experiment. And so if you follow this YouTube link down here on the bottom, there's a very good video showing how the cathode ray experiment works. So, but in short here, what a cathode ray tube is you have a negatively charged cathode and a positively charged anode. And then so there's a beam that flows from one to the other. And so it is found that this beam here is able to be deflected by a magnet. So if you put the positive pole of a magnet towards that beam, that beam of material here will be deflected up towards that positive pole. Whereas if you put the negative pole of the magnet to it, you're going to show a deflection away from itself. Okay, so I might have said battery there. This is a magnet, so positive and negative pole of a magnet. Okay, so what we found here is that this material here is extremely small and has a negative charge. And so the negative charge we know because it's attracted to a positively charged plus pole of a magnet, and it's repelled away from the negatively charged negative pole of a magnet. So the Thomson believed that the deflection should depend on three factors. One is the strength of the magnetic field, so the strength of the magnet you use, the size of the negative charge on the material, and the mass of the material itself. So from this seminal cathode ray experiment, he was able to determine that that beam of light that goes from the cathode to the anode there is actually a flow of a subatomic material called the electron. And so he was able to determine that the mass to charge ratio of this electron within that cathode ray beam was this impossibly large number here, 1.758 times 10 to the 8 coulombs per gram, where the E here is the magnitude of the charge on the electron, and M is the mass of the electron. So the cathode ray experiment can only measure this charge to mass ratio, but not the individual charge of the mass of the electron itself. So this cathode ray experiment by Thomson was very important because it first showed the presence of this negatively charged super small electron. The next important experiment was completed by the American R.A. Millikan, who set out to determine the mass and the charge of the electrode, or of, that should be of the electron, using an oil drop experiment. Okay, so Millikan's experiment showed that you have this oil here, a fine oil that's sprayed into this closed box as a very fine mist. And then there are two different plates here. So you have a positively charged plate and a negatively charged plate, and a tiny hole that's bored into the middle of this positively charged plate. And so this tiny hole allows for this oil droplets to fall down in a single file line between these two plates. And as those oil droplets fall down a straight line, Millikan was able to look through this telescopic lens here to determine the terminal velocity of each of those droplets. And so he used that to determine the overall mass of each droplet. There was another opening into his box where Millikan was able to blast in X-rays that would irradiate these drops as they go down. And so this irradiation actually imposed this negative charge onto these droplets. So once a negative charge was placed on those droplets, he was able to induce an electric field between these two charged plates. So negative on the bottom and positive to the top. And we know that negative charges repel and negative and positive charges attract. So as you do an electric field here, you're going to have repulsion away from this negative plate. And so by tuning the electric field between the negative and positive plates, he was able to deflect up this negatively charged particle such that if he fine-tuned this electric field, he could get that part of these negatively charged oil particles to totally stop in the middle between these two plates and hover in the middle of space. And so this hovering of that particle, through hovering this particle, he was able to actually determine the charge on an electron. Okay, and this is because the X-ray irradiation actually caused there to be a -1 charge due to the presence of an extra electron. So, since the mass of the oil drop and the electric field of the plates was known, Millikan was able to show that the charge on the droplet was always a small whole number multiple of this value that he called E, which is 1.602 times 10 to the negative 19 coulombs. So an impossibly small charge on this electron. Okay, you don't need to memorize that number or anything. Any of these constants would be given to you. So substituting the value of E into Thomson's ratio reveals the mass of an electron to be 9.109 times 10 to the minus 28 grams, which is 2,000 times smaller than that of the smallest atom we know of, which is the hydrogen atom. So the final of the three experiments that are key for our discovery of the constituent components of an atom is the gold foil experiment that was completed by the New Zealand physicist Ernest Rutherford. And so this was used to determine the presence of a nucleus. So the Rutherford experiment, what we have here is a very thin piece of gold foil that is a very thin piece of gold foil that is being irradiated by what are called alpha particles. Okay, so alpha particles, these are a massive little bit of radiation. It's actually, we'll determine this in a few lectures, it's actually the nucleus of a helium atom. And so this irradiation of a beam of alpha particles is passed through this very thin layer of gold foil. And what we do is we surround this gold foil with a sensing strip that is able to determine collision events. And so what Rutherford did was determine where in this 360-degree circle here, where were these alpha particles hitting? So Rutherford determined that most all of the particles passed directly through the gold foil and hit at the very back of this sensing plate. And then there was a small component that was deflected slightly to the side, and then an even smaller component that were totally deflected straight backwards to towards the source itself. So this was a very curious result here. So what would actually cause this deflection, either in a sort of a 20-degree angle or this total deflection backwards towards the source? What could cause that? So for this sort of idea, I like you to kind of envision that there's a bowling ball hanging in the middle of the room. And so you have this bowling ball and you start to chuck golf balls at it. Okay? So most of the golf balls that you're chucking at this bowling ball are going to totally miss the bowling ball. It's going to pass straight through and hit the other wall of the room. Whereas every once in a while, you're going to hit just slightly on the side of that bowling ball, and that's going to deflect it off at a very narrow angle. Okay, so like a 10 or 20% deflection. So that would be this angle seen right here. So that's just glancing your golf ball off your bowling ball. But every once in a while, you might get a really accurate throw and smack that ball, your golf ball, right off that bowling ball, and it's going to knock back towards yourself. Okay, so that's in essence what's happening here. We have this very thin layer of gold foil that's only a couple atoms thick. And as you pass these dense alpha particles through it, most of them are going to pass straight through the foil undeflected. Whereas every once in a while, some of them are going to glance these very massive hard nuclei that we can think of as the bowling balls and could be slightly deflected off course. And every once in a while, you're going to have an alpha particle that's going to collide straight onto this very massive center core and be deflected back towards itself. So this showed that the material, that most all of the material, since most all the events were passed straight through, that shows that this gold foil itself is mostly empty space. But it's only composed of a couple very hard, dense cores that can be able to deflect these alpha particles. Okay, so this showed that atoms are almost entirely empty space, and that the mass of the atom is concentrated in a very tiny central core that we call the nucleus. And furthermore, we determined that this nucleus is positively charged. So therefore, it can repel positively charged alpha particles. And so if we take a look at an atom itself, most of that atom is going to be negative, empty space where these negatively charged electrons with extremely small mass are residing. And there's going to be a very, very small positively charged nucleus. So if you think about an analogy I like to use in order to sort of illustrate how small the nucleus actually is as opposed to the sort of empty space where the electrons reside, think about a giant indoor dome. Okay, this giant indoor dome, it would be the empty space in which these electrons are able to move around. The size of this dense charged nucleus would be the size of a pea located in the center of this giant dome. Okay, so really that did a good job for me of painting the picture of how small these nuclei actually are. So now we have a lot of information about atomic structure. So the nucleus is actually composed of two different particles, protons and neutrons. All right, so we see protons shown here in red, and we have neutrons shown there in green. So protons are around 2,000 times more massive than the electrons. And so these electrons, remember, are going to be moving around this sort of empty space here. But these protons are much more massive than the electrons, and they carry a positive charge equal to that positive E. Remember that Millikan determined that charge of E. Whereas neutrons are almost identical in mass to protons, but they carry no charge. So protons and neutrons have the same mass. Protons are positively charged, neutrons have no charge. Electrons basically have no mass, they're very, very small, and they carry a negative charge. So the number of neutrons in the nucleus is not directly related to the number of protons in the nucleus. So you can have different numbers of protons and neutrons. But the number of electrons is equal to the number of protons in a neutral atom. Okay, so since protons have charge of plus E, and electrons have a charge of minus E, if you have an electrically neutral molecule, or an electrically neutral atom, it means that those number of electrons and the number of protons have to equal each other. And down here is just a table that sort of shows a comparison of each of those materials. Here we can see the charges of both the electron and the proton are the same, just opposite sizes. So elements differ from one another by the number of protons in their nucleus. So the number of protons that a certain atom has determines what type of element it is. So as I said previously, the number of neutrons does not matter for element identification. So all atoms of a specific element have the same number of protons in their nucleus. So we have a value called the atomic number, which is given the symbol Z. And this atomic number is the number of protons in the atom's nucleus. And so that's the same as the number of electrons for a neutral atom. And then we have a mass number, which is given to us by the symbol A, which is the sum of the number of protons, again, which is the atomic number, and the number of neutrons, which we give N, in an atom's nucleus. So the mass number is equal to the number of protons plus the number of neutrons. Okay? And this makes sense because remember, the electrons have such a small mass that they really don't contribute to the mass of a material. So the way that we write we represent a specific atom carries this sort of symbolic notation where we have our elemental symbol, so that is that 1 or 2 letter symbol that you'll take off the periodic table. The value on the top will be the larger of the two as a superscript here. That's going to be our mass number, so that's the number of protons and neutrons together. And down here on the bottom, that's going to be your atomic number, which is the number of protons, which is also the number of electrons for a neutral atom. So, what are the mass numbers for the following? Write using the proper symbolic form. Okay, and so I encourage you guys to pause your video right now and try to actually write this symbolic notation with the mass number as the superscript and the atomic number as the subscript. So I'll write these answers up here for you. So carbon atom with 7 neutrons. Okay, so if we take a look at our periodic table of elements, so pull out your periodic table, there's one in the front of your textbook, and if we take a look at carbon, we'll see that when we take a look at the periodic table of elements, there is a large number that's going to be associated with each of your different elements. So hydrogen has number 1, helium has number 2, lithium 3, beryllium has 4, boron has 5, carbon has 6, etc., etc., etc. Those large numbers that are associated with each atom are the atomic number. So that's going to be the number of protons. Okay, so if we're looking at a carbon atom, if we open up our periodic table, we see for carbon, we have an atomic number of 6. So that means that there are 6 protons. And so if the mass number, so again here, down on the bottom, that's going to be your atomic number, which is going to be your number of protons. So the number that's located up here on the top, that's going to be, again, our mass number. And so the mass number is going to be the sum of our protons and neutrons. So here, for this example here, we have a carbon atom with 7 neutrons. So we have that value is going to be our atomic number, which is 6, plus 7 neutrons. So that's going to give us a value of 13. So the answer here for the first one is carbon with a 13 on the top and a 6 on the bottom. So working through the other ones, helium atom with 2 neutrons. We have helium is a 2 on the periodic table and 4. Hydrogen atoms with 0 neutrons. We have hydrogen, which is H. We see that is a 1, and 1 plus 0 is 1. We have the hydrogen atom with 1 neutron. That would be our H. Again, it is 1 atomic number. 1 plus 1 equals 2. And then a hydrogen atom with 2 neutrons. We have our H, again, an atomic number of 1. And 1 plus 2 is equal to 3. Okay, so for each of these materials, we can see the symbolic representation for each. So, except for hydrogen, all of these atoms contain at least as many neutrons as protons. But we observed here for that hydrogen that we had 3 separate symbolic forms. Okay, and so all of these are still hydrogen because they have, so write these back on the board. We have H1, H12, and H13. Okay, all 3 of these are individual forms of hydrogen. You can tell they're all hydrogen because they all have the H symbol and they all have an atomic number of 1. How they differ from each other are the mass numbers here on the top. And so that just tells us that there's a different number of neutrons in each. So what these different forms are called are isotopes. So isotopes are atoms with identical atomic numbers but different mass numbers. So if we take a look at these isotopes here, the thing that changes between them is the number of neutrons. So changing the number of neutrons does not change the chemical reactivity of an atom. The chemical reactivity is determined by the number of electrons, which we'll get to later. So if I ask all of you to write the symbolic representation for nitrogen 14 and nitrogen 15 isotopes. So when you name an isotope, you state the mass number as the number after it. So nitrogen 14 would be a mass number of 14 and nitrogen 15 would be a mass number of 15. So what we have here for nitrogen Nitrogen 14 is going to have our nitrogen symbol N. We look up on the periodic table and see our atomic number is 7, and then we have a 14 total mass. And so if I ask you guys to determine here what is the number of protons, electrons, and neutrons, here we can see with our atomic number 7, we have 7 protons. Our number of neutrons will be our number of neutrons add together with our number of protons to get the mass number. So 14 minus 7 is equal to 7, so there will be 7 neutrons. And then our number of electrons, since this is an electrically neutral molecule, we would say that there is 7 electrons. So that would be the representation for nitrogen 14. Now, if we want to take a look at the representation and number of each for nitrogen 15, again, we're going to take a look at our symbol N. Atomic number from the periodic table is 7, and we know our mass is 15 because it's given up here in the isotope name. And so if we state now the number of protons, neutrons, and electrons, we see that there's 7 protons given to us by our atomic number. Our number of neutrons is going to be our mass number minus our number of protons, so that's going to be 8 neutrons. And our number of electrons, again, since this is electrically neutral, the number of protons equals the number of electrons, so 7 electrons. Okay? So moving on now. How many protons, neutrons, and electrons are in this chromium molecule? So take a moment to try to do that yourself. So the answer here is we have for our CR24, 52, we can see our number of protons is 24, which is given to us by our atomic number. Since this is a neutral molecule, we know that the number of electrons are also going to be 24. Okay, if it was not neutral, we would see a symbol up here in the upper right-hand corner. We'll get to that soon, but we don't see any symbol, so we know it's neutral. And then for the number of neutrons, we simply do our mass number, 52, minus our atomic number, 24, and that's going to give us a value of 28. So that means we have 28 neutrons. That easy. So this now brings us to molecules where the charges are not neutral. So ions are charged particles resulting from the gain or loss of one or more electrons. So we have 2 different types of ions. An anion, which is a negatively charged particle resulting from the gain of one or more electrons. And then a cation, which is a positively charged particle resulting from the loss of one or more electrons. Okay? And so my high school teacher, Mrs. Runyon, she taught me way back when. She loved cats, so she thought cats were a very positive thing. So cations are positively charged particles. Okay, so I am all for using sort of weird analogies to memorize these different terms. Okay, so if we take a look first at our anions, so they are negatively charged particles resulting from the gain of one or more electrons. And we know that electrons are negatively charged particles. So if we add a negatively charged electron, so for example, if we look at turning chlorine into the negatively charged chloride anion, we take chlorine, which is neutral. If we put an extra electron on it, that's going to put another charge on it to form Cl-. And so this minus is a superscript to the right, which means that there's one extra negative charge. An oxygen atom, if you add 2 electrons, forms into O2-. And this 2- here shows that there's 2 extra electrons. So it's a doubly charged anion. Cations are a positively charged particle. And so this is caused by removing an electron. So if you remove a negative, what you get is a positive. If we added another positively charged particle, which would be a proton, what would happen is we'd actually change the identity of the atom itself. Okay, so if you take carbon and you added another proton to it, so carbon has an atomic number of 6. If you added another atom to carbon, or if you added another proton to carbon, it would have an atomic number of 7, and in that case it'd be nitrogen. Okay, so you can't change the number of protons to impart a positive charge, you just have to change the number of electrons. So by removing an electron, you can impart a positive charge. So if we take a look at the sodium atom, Na, can be turned into positively charged sodium ion by removing one electron. So we have Na+, which shows a singly positive charge, or one less negative charge. A magnesium ion, if you rip away 2 electrons, you get Mg2+. And so that would mean we've removed 2 electrons, so it has this 2+ positive charge. So if I ask you now to work out how many protons, neutrons, and electrons are in the chloride 37 ion. Okay, so that's going to have a -1 charge. So again, we're going to write up our symbolic notation and then put the number of protons, neutrons, and electrons. So our symbol for chloride is Cl. If we look on our periodic table, we'll see the atomic number for chlorine is 17. And so chloride 37, it tells us that our mass number is going to be 37. And a chloride with a -1 charge, that means you're going to have a minus as the superscript on the upper right-hand corner. So if we work up our number of protons, neutrons, and electrons, we can see that there's going to be 17 protons. Our number of neutrons will be 37 minus 17, so that's going to be 20 neutrons. Okay, and the number of electrons, what we have here is for a neutral molecule, the number of electrons would be equal to our number of protons. But here we have an extra negative charge. So that means that you take your 17 electrons plus 1. So what we have now is 18, so we have 18 total electrons. Next, how many protons, neutrons, and electrons are in the aluminum 27 ion that has a 3+ charge? So again here, we're going to be taking a look at our symbol, which is Al for aluminum, and the atomic number here is 13, and given to us here is 27 for a mass number, and then our 3+ charge will be shown up in the upper right-hand corner. So our number of protons will be 13, which is our atomic number. Our number of neutrons, you take our mass number minus our atomic number, so that's going to be 14. And then our electrons, for a neutral molecule, it would be 13 electrons. But here we have a 3+ charge, which means that 3 of those electrons have been stripped away. So if we subtract 3, that leaves us with 10. So now we have 10 electrons. That's it for the day.